Okay, so welcome back. I'm happy you survived yesterday talk and lots of definitions. Today we'll go into applications and we will be solving some nice problems. I already put second set of exercises on the web page. So the first set was about notions of graph limits, graphon convergence. The second set is basically solving problems using flag algebras. There will be no more sets of exercises. The second set is, I think, more interesting because it's exactly what we will be doing during these lectures. If you have time, I encourage you to try to solve those problems from the second set. And on Friday, it seems I will have still some time. I can discuss solutions so that you will maybe learn something from it or check your solutions. Okay, but now let's go to today's talk. Yesterday, I finished with defining what's this averaging operator. Yeah, and earlier we did multiplication. I want to emphasize that it's not the case that averaging after multiplication is the same as averaging and then multiplying. So this does not hold in general. Even if A equals B, so for two elements from the same algebra, it's not necessarily the case. Okay, so remember that if you're taking averaging after multiplication, you cannot use such equality. Let's do some example. Let's consider the same graphon I was using yesterday intensively. So I have two parts which are clicks and the rest is 0. And now let's compare the following product. So rooted edge, like degree of the vertex, and square the average, and the product after. Firstly, averaging and then multiplying. Okay, so what's this? You already know how to multiply. Yeah, we were learning it. So I have two random vertices. They need to be connected with my root. I have two options. And in each case, this coefficient is 1 because whatever vertex I will choose here, I will get an edge. I will be connected with my root, and the remaining one is also connected. Okay, so now if I average this, what I'm getting from the first part, I'm getting a cherry. And now the coefficient here was, let me recall, probability that if I choose a placement of the root randomly, I will see this picture. Yeah, this graph. So in one option out of those three, I see this graph. Yeah, you agree? Yeah, so it's this. While here, wherever I will pick a root, I will see exactly a triangle with rooted vertex. So the coefficient here is 1. Okay, so we express this in terms of graph densities. Now we can calculate it here. Cherry does not appear at all. Yeah. Okay, and the triangle, in order to find a triangle here, I need to have either all three vertices in the first part or all three vertices in the second part. So I need to have like 1 over 3 cube plus 2 cube over 3 cube. You agree? Oh, come on, I haven't lost you. At least one person can see and use your head to confirm me. Good. Okay, so what's this? This is 1 plus 8, it's 9. I divide by 27, so it's 1 over 3. All right? Good. Of course, one can calculate it directly from here. I mean, what's this? If you remember, this was degree distribution. So it was with probability 1/3. It's 1/3 with probability 2/3. It's 2/3. If I square it, I have with probability 1/3, 1/9, and with probability 2/3, 2/9, 4/9, sorry. So if I calculate it, it's exactly the same. Okay, and here, if I use this averaging, I get just edge density from here. Yeah, and the coefficient is 1 because wherever I place the root, I have exactly this times the same. And what's the edge density here? In order to find an edge, I need to have two vertices in the same part. So it's 1/9 plus 4/9. And I multiply by the same. It's 5/9 squared, 25/81. Yeah, and you can easily see that this is something completely different. Even despite the fact that I was multiplying the same element. Okay, so that was practice of the calculations that we were learning yesterday and also checking this. In general, a useful inequality comes from Cauchy-Schwarz. So for any labeled graph, graphon you will remember that all those computations are in some specific graphon. Yeah. Any two elements from my algebra. What I have is that the product and then averaged is at most firstly square of the second one. If you think about it, this is exactly the known Cauchy-Schwarz inequality, because this is like squaring sum over all products. Yes, and this is less than equal than sum of squares of the first elements times sum of squares of the second elements. Yeah, this is like a Cauchy-Schwarz inequality. In particular, if I take B with just my root, then I get a very useful inequality that A average and then square is less or equal than NA squared and then average multiplied by the averaging of my root. Yeah, root square is still root. There is nothing to choose. Okay, and this inequality will be useful in some applications later. Okay. Are there some questions? No. So let me move it up. And let's try to prove something. Okay. So we have this Mantel theorem, right? Mantel theorem says that any graph, triangle graph, and vertices at most square over 4. Yeah, this is Mantel theorem for graphs. An equivalent for graphons would be, I'm assuming that my triangle density is 0, and I would like to obtain that my edge density is at most half. Yep. So this is what we will be trying to prove first, and then use theorem for graphons to obtain theorem for graphs. Okay. So I will start with a easy, maybe just let's say true inequality. If I take any expression, for example, like this, and square it, this is square of some probabilities. In particular, it's non-negative. Yeah, and if I average, so it's just summing up over all possible placements of the root, it's still non-negative. Yes, definitely I can write that this is a true inequality. Okay, let me read it. It's just edge with a rooted vertex minus non-edge with a rooted vertex. Okay, so let's compute what it gives. This, let me do it slowly. So I have this minus 2 times this plus non-edge. Non-edge, everything is average and greater or equals. We know how to multiply this. Yeah, I even did it somewhere, okay, over there. So this is triangle plus cherry rooted on the central vertex. Okay, if I multiply those two, I get this and this graph. And what's the coefficient here? So it's a probability that among those two vertices, I pick one at random and I need to see an edge and the remaining one non-edge. So here it's happening with probability exactly half. But I have these two here. So 2 times half is 1. That's why I don't need to write here anything. Okay, and then multiplication of those two. So I have 2 graphs like this. And now the coefficient is 1 because whatever I will choose here, it creates me what I need. Okay, so now averaging. Averaging this gives me just a triangle, and the coefficient is 1. This is already what we did. From here, I get a cherry with coefficient 1/3 because there is one option out of 3 to choose the root. Here I get complement of a cherry, this 3 vertex graph with 1 edge. And what's the coefficient? I need to place a root here in a way to see this graph. So I have 2 options out of 3. Yep. So it's 2/3. Here is similarly 2/3 cherries plus this is just this guy. And here I have complement of cherry. And the coefficient is 1/3 because I need to choose root here. Is it clear? Okay, so I obtained such inequality. Let me group it. So it's triangle plus minus 1/3 of the cherry. Yes, minus 1/3 of this graph plus 3 independent vertices. Okay, I will try to fit here. But what's my goal? My goal is to bound density of edges, right? We were learning already that I can express edge in terms of densities of 3 vertex graphs. Yeah, it was yesterday. So I can express edge as triangle plus 2 times cherry plus 1/3 of this guy. Yeah, you remember? It was something like this last time. Okay, so what I do, I want to add this inequality here with coefficient half. So I will say that this is at most, and now add half of this. Okay? What I will obtain? Triangle plus half of the triangle will be 3 halves. triangles. Now 2/3 of a cherry minus 1/6 of a cherry, which is 4/6 minus 1/6 is half. You agree? Good. What's happening then? 1/3 of this graph minus 1/6 of it, which is 1/6. Right? And the last term is just half of this. What I can say now, if I take out triangle, then the rest is just half triangle, half this, less than half, and half. So definitely it's less than triangle plus half of everything. Yeah, you agree? Yeah, half of everything, like everything, those are probabilities. So they sum up to 1. So half of everything, so half of sum of those, I get exactly 3/2 triangles. This one, this I overestimate, and this is actually. Okay, so now look at what we want to do. We have a triangle is 0, so this is 0, which means that this is half. And they obtain exactly what I need. Edge density is less than half. So we have the theorem for graphons. Yeah, is it clear? Basically, I just did some computations as we learned yesterday. But if you would like to read it formally, then this is some multiplication of probabilities of densities, averaging over all choices, etc., etc. But basically, this computation is showing what we need. The Mantel theorem calls for graphons. Some questions? Okay, let me move here. We proved Mantel theorem for graphons, but we are interested in graphs, right? We would like to have Mantel theorem for graphs, not for graphons. So how to do it now? Let me do the following trick. Imagine that Mantel theorem for graphs does not hold. What does it mean? It means that there exists some finite counterexample. Some graph, so there exists, assume Mantel theorem does not hold. Okay, so we have some finite counterexample. We have G such that G is triangle free. Let's say that G is K vertices and G has a number of edges which is above the threshold. So it's at least K squared plus 1/4. Okay, a bit above. What I want to do now is from such a single counterexample, create a bigger counterexample, then a bigger one, etc., and obtain a sequence of counterexamples. And if I have a sequence of counterexamples, I can calculate its limit. And I want to obtain counterexample in the limit, but for limits, we already proved that there cannot be a counterexample. Okay, that's the idea. So how now to construct a sequence of counterexamples from a single one, despite the fact that we have completely no idea how it looks like. Okay, so what I do, I consider my sequence of graphs, which are blow-ups of G. How a blow-ups works. So imagine that you have this graph G somewhere here, looks somehow. And now, instead of every vertex, I put a blob. Each blob will contain n vertices. And for every edge, I put complete bipartite graph. So all possible edges accordingly to edges in G. Okay, you understand the concept? So G1, it will be exactly this example G, and then I blow up the vertices. Okay, so I want to argue that each such graph is a counterexample. So first, if it's triangle-free, if I'm blow-upping vertices, I cannot introduce a triangle. I'm not putting any edges inside, so if there is a triangle, it needs to exist in the first graph, but we know that there was none. Okay, so it has no triangles. What's the number of vertices in my GN? So every vertex, and I had 30 vertices at the beginning, now becomes n vertices. So I have k times n vertices. And what's my number of edges? Whenever I had an edge in graph G, now I have n times n edges. So I have k squared plus 1 over 4 times n squared edges. At least. You agree? Okay, so what's my edge density? In order to calculate edge density, I need to divide number of edges by number of vertices choose 2. And this is at least k squared plus 1 over 4 times n squared divided by, and here is kn choose 2, but kn choose 2 is less or equal than kn squared over 2. So I can write it like this. Okay, and now n squared will disappear, and I will obtain here k squared plus 1 over k squared. You agree? I missed something. 2. Now it's fine? Okay, in particular, this is strictly bigger than half. Okay, I have sequence of counterexamples. And now I go to the limit. Firstly, you can ask me, okay, if the sequence is convergent and if if I can go to the limit. Firstly, I don't need to even know if it's convergent, because every sequence growing or every sequence contains a convergent subsequence, so I can consider just convergent subsequence. But if you need, you can also prove it that sequence of blow-ups is always a convergent sequence. Okay, so I have a convergent sequence of growing orders, and from the first lecture, we know that there exists a limit. There exists a graphon, which is the limit of this sequence. So what this limit graphon satisfies? Since each graph here was triangle-free, then in the limit, the density of triangles is 0, right? We cannot create suddenly positive density. The definition of convergence was that density of every graph, in particular triangle, in my sequence need to converge to density of triangles in the limiting graphon. So if this was 0 all the time, so in the limit we also have 0. Perfect. And what's my number of edges? Here I prove that the density of edges is at least this number, and this is some fixed number, right? K was fixed number of vertices in my counterexample. So in the limit, my edge density in the limit is tending to something which is still at least k squared plus 1 over 2k squared, which is strictly above R. And this contradicts the theorem that we just proved. Okay? So in total, it means that there cannot exist any single counterexample for Mantel theorem, and we prove Mantel theorem. Yeah, for every graph. So this is what I want to emphasize, that many people think that graph limits are for showing some statements for arbitrary large graph or for asymptotic statements. But no, I've just shown a theorem for every number of vertices. Yep. And this is a general approach that it's often useful in this setting. So imagine you have a conjecture or a problem that you want to solve, and the problem is for graphs only, like Mantel. So what you do is firstly you write this problem in the language of graph limits, then you prove it there, for example, using flag algebras or other limiting methods, and then you create a sequence of hypothetical counterexamples to obtain a counterexample in the limit, which gives a contradiction, so there do not exist any single counterexample. You see the general procedure? Perfect. Of course, I'm sure you knew Mantel theorem earlier, and you are able to prove it easy. Here I did it for like 20 minutes. But there are some problems that were open for 20 years, 30 years, and we were not able to prove them. While after introducing this method, those problems become just easy exercises that I could give you. Okay, this is open problem for 30 years. Now you can solve it in 5 minutes. Yeah, because it's just translated to graphon setting, doing some easy computation, and then considering this sequence of hypothetical counterexamples. That's the powerful part of the method. There is one more thing I should mention, and you can ask, why the hell I started with this inequality, right? This was the only weak point. Maybe we should rotate the camera. Yes, so this was basically the only place where I did some intellectual thinking, right? Everything else was here just mechanical calculations that could be done by a computer. Yeah, so this was the only place where I was thinking. And then this reasoning of taking a blow up of a counterexample, this is standard reasoning. So if you have idea how to come up with starting inequality, then you basically have a proof. Yeah, this was the only place which is not mechanical. And what I want to do now is to convince you that this part can also be done mechanically. I can ask computer to find me the best inequality to start with, and then obtain the rest of the proof. So in other words, I would like to create the automatic approach, which will be just, okay, I want to prove Mantel theorem, press a button, and then computer will find the inequality, obtain this, and give me proof. You understand the idea? Perfect. Okay, so this inequality can be written in a bit different form, in a matrix form. So I took basically a vector containing those two graphons, those two flags. I multiplied by 2 times 2 metric, and multiply by the same vector from the other side. And I, after arranging, claim that this is at least 0. The matrix here was 1, 1, minus 1, minus 1. And if you do this multiplication, you will see that this is exactly this inequality. Yeah, because edge, rooted edge squared, which comes from this place in the matrix, is here. This minus 1 comes from multiplying the different elements of the vector, and this plus 1 gives me multiplication of this. Yeah, so this is basically such kind of inequality. And why this inequality is true? Because this matrix, we call it Q, is positive semi-definite. What it means that the matrix is positive semi-definite? It means that whatever vector I will take and multiply this matrix from both sides by such vector, I will obtain something which is non-negative. Okay, so instead of this matrix, I could take here any metric which is positive semi-definite, and I will obtain true inequality, something which is always at least zero. Other characterizations of positive semi-definite matrices is, for example, that all eigenvalues of such a metric are non-negative. If you calculate eigenvalues here, one is positive, one is zero, so it's fine. And this is the general approach I would like to do. So let me move back here. So say we want to solve some problem, like maximize some function on graph density, right? In our case, this function g was just edge density. In general, it can be whatever you want. Like, for example, in Goodman's bound is triangle density plus density of the independent three vertices is at least quarter. So here, if I maximize, I can put, for example, 1 minus. Yep, in order to minimize, to find the minimum here. And then you can, any extremal graph theory problem in those graph densities expressed as maximizing of some function. Then I do fix some number n, integer, and this is basically saying on how big graph densities I'm doing my computations. Here, everything I expressed in densities of 3 vertex graphs. Yep, so this is my n. So in our case, it was n equals 3. So let me be writing in the parentheses what was happening there. Then I express this function g in a sum of all graphs with all graphs on n vertices, yeah, with some densities gh. So this is done here. Yeah, I express edge as sum of triangle density plus 2/3 cherry plus 1/3 of complement of a cherry. Okay. Notice that. Okay, let me write it. So it was this. Note that I can. Let me move on beside. I know that triangles are 0, so basically, erase it. What I can do, I can now maximize this g. So this is maximizing the sum. By just looking at maximum of every of those. So it's just maximum, sorry, maximum over all age of GH, right? If I need to sum up something, I can bound every by the maximum and just use just that the sum of all age in the class is 1. And this way, this, in my case, would be just bounded by 2/3. Yeah, because the biggest coefficient here is 2/3. This is not a good bound. In Mantel's theorem, we want to obtain half. So easy approach like this, naive approach, gives me 2/3. But what we did there, what we can do in general, I want to add to my G those inequalities of this type, right? So this was done here. So I want to add inequalities coming from some positive semi-definite matrices. So what I'm doing, I'm considering some fixed labeled graph. In my case, it was just a rooted vertex. Then vector of all graphs and flags. Time bounded size. So let me write it. I take size m, which is at most n plus size of r/2. I will explain later why exactly this. So in my case, this was size of my flags. I consider this 2. Yeah, I consider flags of size 2. R is m is 2. And now I consider vector of all flags which are of size m and are rooted with this labeled R. So in case there, it was the vector consisting of a rooted edge and rooted non-edge. Yeah, this is all flags on 2 vertices with this root. Okay. Then I assign some variables Uij for each pair of flags. Pair, let me call it Fi, Fj in this. Yeah, so I will have, in my case, 3 variables. Yeah, one for pair consisting of 2 times this guy, one for the different one, and one for 2 times the non-rooted edge. Okay, and now if this metric over all ij denoted by Q, if this metric is positive, semi-positive definite, then we have the inequality that we want. So we have that if I multiply vector v times my matrix times the vector transpose, which is just the sum over all those elements, all those flags. Coefficient times the multiplications of those two. I have that this is non-negative. Right? So in my case there, I consider specific matrix. It was containing like ones in the diagonal and minus ones everywhere else. This metric was positive semi-definite, so I can use the inequality that after multiplying by any vector, I have something which is non-negative. Let's remove that. Okay, so what I do, I average. We know that this is at least 0, so I can average it. This is exactly what I was doing there. And I can express this as a sum over all graphs on n vertices with some coefficient. We call me this coefficient CH. And now, what's the size here? Those vectors were of size n, which I took at most n plus size of my root over 2. So if I multiply those two things, how big flags I get? It's this times 2 minus size of the root. Yeah, because in such a flag, r vertices are rooted, so n minus r over 2 are unrooted. If I multiply two such flags, I get this many vertices. So twice the number of unrooted vertices that I need to take at random, plus the rooted vertices. Yeah, and this is explaining why I took there at most this number, so that after multiplication, I fit in graphs on n vertices. And okay, so we have inequality that some linear combination of graph densities on n vertices is at least 0. So I can sum it up to about the expression defining this G. If I sum it up, I get that G is at most sum over all graphs on n vertices, and now I have CH plus GH. Yeah, I also forget that. Expressing G as sum over all densities with some coefficient. Okay. So what I have now, I can similarly as before bound this by maximum of all the coefficients. And so by each of the graph, I'm bounding this by the maximum. So I have sum of all h, and this is 1. So this is maximum over all coefficients. Yeah, and this is what we have done in Mandel's theorem. So I use this inequality. I use the definition of multiplication and averaging to express it as some linear combination. Yeah, it's here. Yeah, I have some linear combination of graph densities. And then I sum it up with my expression of G. This is here. Yeah, I sum it up, I get this inequality. And finally, I bound it by maximum coefficient that appeared here. Yes, so triangle is 0, this does not exist, and here the maximum coefficient is half. Yeah, and this gave me exactly the bound I needed. Yeah, so the good thing is that if I express this, then those some of those coefficients can be negative, some can be positive, like in the inequality that we have here. And if I write a good inequality at the beginning, then the negative coefficient will reduce the maximal coefficients that appear in the expression of G. Right? Here, for Manta, we're using that edge is like 2/3 of a cherry, and 2/3 was too big number. And in my inequality here, you see that cherry is with negative coefficient. That's why make it smaller up to half without enlarging other coefficients too much. And this is how it works. So what I can do now, I can use optimization. It's called SDP, semi-definite programming. It's a numerical method which allows to minimize or maximize some linear expression under conditions which are linear, involving some matrix which is positive semi-definite. So what I can do now, I can ask the computer, this numerical method, to find the best bound, which means minimize this expression, right? I want to find the smallest possible upper bound. So in my SDP, I write minimize this expression under condition that the matrix Q, which is giving me those coefficients CH, is positive semi-definite. Yeah, you understand the idea? And so I just write to the computer, okay, just give me minimum possible bound, upper bound you can find, assuming that you use positive semi-definite matrix. And if the computer is using positive semi-definite, then everything what was written is correct. It gives me true inequalities, and I obtain a true bound. I can do even better. From here, I consider a single root and a single matrix related with this root. What I can do, I can consider various different roots, various different labeled graphs. Yes, for each of them, take a different positive semi-definite matrix and write all those inequalities for each such matrix and just sum them up together. Yeah, you understand? I can use more matrices than just one. So in particular, yesterday Paul mentioned the problem of maximizing pentagons in triangle-free graphs. And this was one of the examples where the method became powerful. So this was open for like, I don't know, 28 years or something like this. And what you can do here, you can consider as those labeled graphs. Let me go close slowly. So I take n equals 5. So express everything in terms of 5 vertex densities. So in case of pentagon, I have nothing to do. Then as my labeled graphs, I take 3 possible options. So I take rooted cherry, root this, this. So I have 3 graphs. For each of them, I take m equals 4, which means that there is just one more vertex. For each of them, I take a matrix. Yeah, matrix is of size, just saying in how many ways you can connect additional vertex to the roots. For each matrix, I get an inequality. So in total, I obtain some bound here involving the 3 matrices. I press enter on a computer, and the computer is saying that if you use those matrices, you get a bound which is exactly the bound that Erdős was claiming in the matrices. Okay, and the proof is done. I will show you the full code tomorrow. So basically, solving a 30-year-old open problem is not just by writing 2 lines and pressing enter. Okay, let me pause at this moment. If you have any questions or I went too fast and you want to ask for something, and we will resume in 8 minutes. Okay, we are ready to resume. Before I erase the proof of Mantel theorem, graphons, I would like to emphasize one more thing. Imagine that you not only want to prove the theorem, but you would like to have some characterization of extremal examples. In Mantel theorem, we know that the extremal example is a complete balanced bipartite graph. Yep. So my question is, can we get it from this proof? So take a look where we used inequalities and what will happen if they were equalities, right? So what's happening in the extremal case? So firstly, look at this inequality. And this inequality was that everything else than triangle, which is 0, is bounded by half. Yeah, and when it's equality, when I would need to have like half of those, and half of like the coefficient half by each of them, but here is less. So this is equality only when this graph has 0 density. You're right. Yeah, in other cases, this would be strict inequality. And what it means for a graph that has 0 density of those stuff. If you take any 2 vertices, not connected vertices, they cannot have a neighbor of one of them, which is not a neighbor of the other. So basically, it means that all the not connected vertices are having the same neighborhoods, which means that our graph needs to be complete multipartite. Yep, you can verify it by yourself. If you don't have this graph, then it means that your graph is really complete multipartite. We know that there are no triangles. So there needs to be at most 2 parts, right? So now we know that our extremal example is a complete bipartite graph. Okay, it's still not enough. We want to get that it's balanced. So let's look at different inequality that we used. What this means? This is equality if this inside the averaging is equal, right? Because we have square, averaging is like summing up over all choices. So we need to have that for every placement of the root in my graph, this evaluates to 0. Yeah? What it means that this evaluates to 0, it means that degree of a vertex is the same as non-degree of a vertex, and this needs to hold for every placement of a root, so for every vertex. So every vertex in my graph, in the extremal graph, needs to have the same degree. Right? Degree equals non-degree, so it needs to be half, which means that this needs to be balanced. Yeah. So the proof is not only giving us Mantel theorem, but it's basically characterizing all the extremal examples. For the remaining time of today, my goal is to show you how to set up computer so that it's calculating the thing that we want. Probably not many of you will be writing your own program for computing in flat algebras, but for those who would like to write such a program, this could be interesting to see how to set up everything. So let's still focus on this example. So what we're doing here, we came up with writing that edge density that we want to bound. It's 2/3 of a cherry plus 1/3 of a complement of a cherry plus this matrix. So it's vector rooted edge, non-edge times matrix of coefficients 2, 0, 1, 1 times the vector averaged. Okay, I added the matrix, it's already inequality. Okay, so this is what we obtained, and we want to write this in this form. So minimizing some expression involving coefficients of the matrix. So let's see what's this. This is exactly, let me repeat this. And now I have Q00 times averaging of this multiplication plus Q01 plus 2 averaging this multiplication and Q11 with the remaining one. Right now I use the definition of multiplication. So it's once again what we were doing there. Maybe I will do it fast and just copy from there. So after multiplying and averaging, I get here 1/3 of cherry. Here I get 1/3 of this, 1/3 of the cherry, and here I get this plus 1/3. Yeah, I hope I haven't done any mistake. Somebody's checking. Yeah, so I'm writing triangle density is 0 because we are proving Mantel. So I'm already removing it. Yes, it seems everything is correct. So what I get now is triangle cherry is multiplied by 2/3 plus 1/3 of this thingy. No, I'm missing 2. Yeah, this 2. Okay. Triangle cherry is multiplied by 2/3 plus 1/3 of this plus 1/3 of 2/3 of this. This is by cherry. This is 1/3 plus 2/3 this guy and 1/3 of this guy. And the remaining is just 2, 1, 1. Okay. And now, following this approach, I want to maximize this by the maximum of the coefficients here. So by the maximum of those three. Like this. Yeah, you agree? Okay, so my semi-definite program needs to minimize this expression. Minimize because we want to find the lowest possible upper bound, right? To have the better bound. So it needs to minimize this expression over all coefficients here, forming a positive semi-definite matrix. Yeah, this is exactly what we need from our program. Okay, so now let me try to explain how this positive semi-definite programming works and how can we use it for such expressions. How the semi-definite programming looks like. We take symmetric matrices. For fixed real symmetric matrices. C, then A1 up to AA of size n times n. And vectors B1 up to Bk SDP is the following problem. Maximize trace of multiplication this matrix C transpose times my unknown matrix X, subject to the following constraints. Firstly, trace of multiplication of any matrix from here times my matrix X gives the vector Bi. And X positive semi-definite. So if you open, I don't know, Wikipedia webpage or whatever notebook for numerical computations, you will see this form of semi-definite programming. Just maximize some linear expression coming from multiplying a given matrix by the positive semi-definite matrix that we want to optimize under conditions that some other multiplication of this matrix times given matrices gives the given vector. Yeah, so this is exactly the setup of the SDP program, semi-definite program. So now how to write our problem in this way, okay? Are there some questions? So I have my problem that I want to express in this form. So first, let's say what this big N is. You remember, we were fixing in our problem small n, which was the size of graph densities that we're using. We're fixing small m, which was the size of flags we were using. And here I'm taking 1 plus number of graphs on n vertices plus number of those rooted graphs on m vertices. And so in our Mantel theorem case, it was what? Was 1 plus number of flags on 3 vertices. There were 3. 3 because we don't count triangle. And here I was using vector with 2 flags, right? So this is 2. So all the matrices that I'm considering here will be of size 6 times 6. Now, K, which is the number of the matrices there, will be just this. So the number of graphs on n vertices. And each matrix, its AI, will be looking the same. Yeah, I need to define a 6 times 6 matrix. So in the first corner, for this one, it will be just -1, always. For each matrix, it will be just -1. Then, for diagonal here, the diagonal of size of Gn, I will put 1 on place number I, and everywhere else zeros. Okay, so the first matrix will have 1 here, and the rest of the diagonal this side. Zeros, the second one will have second place, etc. This is for me to emphasize for which graph I'm doing these calculations. And in the remaining place, this place is of size, which is number of flags that I use of this type. So in our case, it's 2 times 2. And here I want to put those coefficients coming from this multiplication and averaging. Yeah, so this is those coefficients that we'll find here. Let me write it, what we have in our case. So in our case, -1 in the corner. Next, I have a diagonal. The first graph we have 1. And then I have here values coming from there. So let's say that this is which one, which graph? Say that this is this graph, which is the last here, and it has only one element of the matrix, and everywhere else 0. Okay, it's Q1, 1. Q. Yeah, same 2. I have -1 here, then 0, 1, 0. And here, this is for this graph, I have this expression coming from here, which is 1, 1, is 1/3. Yeah, the coefficient by this element. And here I have 2/3 for 0, 1. But I don't want to write 2/3 here. I want to keep it symmetric. So we put 1/3 and 1/3. And I put 0 because there is no Q00 by this graph. Okay, you understand? Okay, so in this expression, this was for this graph. Okay, it's here. I have Q11 with coefficient 1/3, and I put it here in place Q11. Then Q00 has 0 coefficient, so I put 0. And Q01 is 2/3, but Q01 is the same as Q10, right? Because this metric is symmetric. So instead of writing 2/3 Q00, I'm writing 1/3 of Q00 plus 1/3 of Q10. So that's why I put 1/3 and 1/3 to keep this metric symmetric. Okay, and the last matrix is -1 here, then on a diagonal in third place 1, and here I have 1/3 in the first place, and similarly as before 1/3, 1/3, and 0. Yeah, you agree? Okay, so these are matrices AIs. Matrix C. Matrix C is very easy. Higher. So it has -1 in this first corner. And everything else zeros. So in this diagonal block, I have 0, and here also I have 0. Oh, I'm not writing here anywhere else, but of course I want to have it zeros. I'm not writing zeros. Not to make this should do it. So this matrix C is just -1 in a corner, nothing else. Okay, and what I need left is those vectors Pi. And for Pi, I just put Pi. This I goes from 1 to k. Right? This is k. So each element of this vector is just for one graph in my in those graphical vertices. Yeah, I have there 3, and for each of them I put those coefficients that are here. But with a minus sign. So my B1 was for this, and for this there is 0. B2 is for this graph. For this graph there I have 1/3. B1 0, B2 1/3, B3 2/3. Yeah, sorry, I want to have it with minus. So in general, Pi is this minus an expression of the thing that I want to maximize by the height graph. Very fine. Okay, so if I do it like this, let's see what's happening. Okay. I'm maximizing trace of this multiplication. Multiplication, yeah, matrix X, I would say. Matrix X let me take x0 for this corner, then x1 up to xk for those diagonals, and here my matrix Q that I need to find. Okay, so now what's this? This matrix C was just -1, right? So if I multiply, then this becomes just minus x0. We agree? Yeah, I multiply matrix C is just -1 in the corner. I multiply by matrix X, which has in this corner x0, everything else, so on. Oh. Now, what's this trace of those matrices times X equals Pi? What it means? So I take this matrix, multiply by X. -1 in the corner gives me minus x0. Then I get plus xi, because I have 1 on the ith place and everywhere else on this diagonal is 0. And then for multiplying those coefficients, by my matrix Q, I get exactly those expressions that are here. Yeah, so I get yeah, in our case, here you write it. For 1, I get just Q00, Q11. And this is equals to B1, and B1 is set to 0. The next one is similarly, and now I have this expression. So it inserts Q01 plus 1/3, 1, and I obtain this minus 1/3. And for the last one, I have this expression. And it gives me B3, so minus 30. Okay? So this is coming from this. And what it means that this matrix X is positive semi-definite, it just means that x0 needs to be non-negative, all those xi's needs to be non-negative, and the matrix Q that I have in the last block is positive semi-definite, as I need in my proof. Okay, and now what it means that X is 0 and xi's are non-negative, that those x's are non-negative for this. If we use it here, like x1 at least 0, I will obtain that what minus, let me move it x0 this side, I will obtain that x0 is this is bigger or equal 0. I'm lost, I need you. And I put that this is at least 0, so I get x0 is at most Q11, or different way. No, at least. Right? I think that this is at least 0. This is at least 0, so this is at minus 0 plus Q11. Is smaller or equal 0 from here. So x0 is at least Q11. Right. From the second inequality, if I use x2 is at least 0, in a similar way, by moving x0 to the other side and moving -1/3 here, I get x0 is at least 1/3 plus 2/3, 0, 1 plus 1/3, 2, 1, 1. And from the last one, in a similar way, I get 2, 3, 2 over 3 plus 1 over 2, 0, 0 plus 2 over 3, 2, 0, 1. So basically, x0 is at least maximum of those. Yeah, which is exactly what I have here. Yeah, which means that this Q00 is upper bounding the thing that I want to upper bound, which means if I minimize x0, I get exactly the best bound I can prove. Okay, and my problem here, like this semi-definite programming, is maximizing this, which means maximizing minus x0, which is minimizing x0, which is exactly what I need. Yeah, minimizing x0 is minimizing the upper bound that I can have for my problem. Okay, so with this setup, I just translate all our problem to SDP, press an enter, and computer is saying me, okay, I can prove you bound half for Mantel, and you are done. Okay, so with this good accent, let me finish and see you tomorrow. Thank you.